In the last couple chapters, we've been focused on quadratic equations and graphing parabolas and finding properties of parabolas. Um, we're continuing with that in chapter 9, but because all quadratic equations have an x squared term in them, we need to focus first on kind of undoing that squaring process, looking at taking square roots. And so the first section in this chapter is going to focus on radicals like square roots and learning how to deal with them mathematically so that we can apply these rules to quadratic functions. So, um, first of all, a few important definitions. A radical is any expression containing any kind of root, a square root, a cube root, etc. The number inside the square root is called the radicand. The index, for the purposes of problems we do, is usually going to be 2 because we're usually going to deal with square roots, but we'll also look at some larger roots like cubed roots as well. And if there is a number multiplying the kind of radical term out front, we call that the coefficient. The next thing we need to talk about is simplest form of radicals. And you'll see why this is important once we start doing kind of addition subtraction problems with radicals. It's important for radicals to be in simplest form, kind of like fractions. In grade school, if you wrote a fraction like 3/6, your teacher would say, you haven't put that in simplest form. You need to write it as 1/2. There's also going to be a simplest form for radicals, where there are going to be no perfect squares or underneath the root if it's a square root, or perfect cubes if it's a cube root. And it's going to be important that the radicand is not a fraction and you don't have any radicals in the denominator of a fraction. So let's look at some examples here and how we write roots in simplest form. Here we're asked to take the number 108 and the square root of 108 and write it in simplest form. And so what we want to do is we want to think, well, what are the factors of 108? Can we find any perfect square factors of 108 and remove them from underneath the root symbol? And so if you are fortunate and kind of spot right away that 108 is the same as 36 times 3, then we can think about that as being the square root of 36 times the square root of 3. And of course, the square root of 36 is 6. And so we do 6 times the square root of 3. And that is simplest form. If you don't spot the biggest square number right away, that's okay. You can do it in a kind of more of a step-by-step process. And when I did this problem in class, most of my students spotted more quickly that kind of uh, uh, 9 times 12 were two factors of 108, and 9 is a perfect square. And so if we go ahead and do this and do the square root of 9 times the square root of 12, well, the square root of 9 is 3, and 3 times the square root of 12 is mathematically the same as the square root of 108. It just isn't fully simplified because 12 can be further split into 4 times 3, and 4 is also a perfect square. And so if we kind of rewrite this as 3 times the square root of 4 times the square root of 3, then we get 3 times 2 is 6. So we get 3 times 2 times the square root of 3, and we end up still with the same answer. So it's okay if you don't simplify the problem all in one step. You can still get the same correct answer in the end. It's important to realize that variables raised to an exponent can also be simplified. If I take this and kind of split it into square root of 9 times the square root of x cubed, students quite often spot square root of 9 is 3. But then they don't really necessarily know what to do with that cubed root of x, the square root of x cubed. If I split this into x squared times x, it's a little easier to see what's going on. The square root of x squared is just x. So I'm left with 3 and x outside of the square root symbol, and the square root of x cannot be simplified anymore. And so my final answer is just 3x times the square root of x. So it is important to realize that the square root of a square number, so the square root of x squared, is just going to be x. Okay, the square root and the squaring processes undo each other. Let's look at a couple more examples. It is important when you're writing square roots to not have a square root in the denominator. Now, these two questions, the square root in the denominator is just going to kind of disappear on its own. We'll look on the next page at how to handle square roots if they don't disappear on their own. When you have a quotient, uh, a fraction inside of your square root, just like here, we were able to kind of separate a multiplication problem into separate square roots. We can do the same thing with the division problem. We can have the square root of 15 over the square root of 64. The square root of 15. 15 is just 5 times 3. Those are both prime factors of 15, so they are not perfect squares. There's nothing I can do to simplify the top radical. But on the bottom, the square root of 64 that's a perfect square. The square root of 64 is 8. So simplest form is the square root of 15 divided by 8. If I look at the second problem, again, I can kind of split this into the square root of 81 on top and the square root of x squared down below. And so I have a square root of 81, that's a perfect square, so I'm left with the number 9. And the square root of x squared, remember the square root and the squaring are opposite processes. They cancel each other out, so I'm just left with an x down below. And this number is now fully simplified. All right, so far, all the examples we've looked at have been square roots. The same rules apply to cubed roots and other larger roots. The one thing that is going to be different about square roots versus cubed roots in Algebra 1 is that in Algebra 1, you will not be asked to ever take the square root of a negative number. Okay. You'll learn how to deal with this in Algebra 2. The square root of a negative number is an imaginary number. Um, and you'll learn how to cope with that in Algebra 2. However, you can take the cubed root of a negative number, because if you think of something like -4 times -4 times -4 equals -64. So if you take the cubed root of -64, that equals -4. Taking the cubed root or an odd root of a negative number um, just gives you a negative number. It's not imaginary the way it is when you take the square root or any other even root of a negative number. So let's look at this example here. If we want to take the cubed root of a number, we're using the same process as before, except instead of looking for perfect square factors of the number under the radical, we're looking for perfect cube factors of the number under the radical. And negative 128, we can get that number negative 128 if we multiply together negative 64 times 2. Negative 64 times 2 is negative 128. And negative 64, as we just kind of discussed up above, is a perfect cube. The cubed root of negative 64 is negative 4. 2 is prime, so it doesn't have any factors that are perfect cubes. And so our final answer is negative 4 times the cubed root of 2. Once again, we can also take cubed roots of variables. So I would write this as the cubed root of 125 times the cubed root of x to the 7th. The cubed root of 125 is just 5. And now we're left with this cubed root of x to the 7th. I'm going to show you the way that I think most students find it easiest to think about it. I'm going to split that x to the 7th up into 3 parts. I'm going to split it up into x cubed times x cubed times just an x left over. So if you think about x cubed times x cubed times x, when you multiply together variables with exponents, you end up adding the exponents together. So 3 plus 3 plus 1 is 7. And so this expression means the same thing as the cubed root of x to the 7th. So how do I simplify this now? Well, the cubed root of x cubed, those two processes undo each other, and I'm just left with x behind. Same thing here. The cubed root of x cubed, those two processes undo each other, and I'm just left with x behind. The cubed root of just plain old x cannot be simplified any further. There's no perfect cube that's a factor of x. And so I'm left with this expression, which I can further simplify a bit just by writing 5 times x squared times the cubed root of x as our final answer. Now, there are shortcuts here, kind of faster ways to think about it, so long as those faster methods make sense to you. For one thing, you can think of this as the cubed root of x to the 6th power times the cubed root of x. So again, I'm looking at just this portion here and a different way to express that. The cubed root of x to the 6th, because 6 is a multiple of 3, um, I'm basically doing 6 divided by 3 gives me x squared then when I simplify this portion. And I'm still left with the cubed root of x left over. The reason this works is because a root is really just a fractional exponent. When I take the cubed root of something, this is x to the 6th um, raised to the 1/3 power. When I take the cubed root, that's really the same thing as raising it to the 1/3 power. Now, our textbook does not give instruction as to roots meaning the same thing as fractional exponents. However, it does make the rules that we learned in chapter 6 more consistent with what we're learning now. And we can see that if we have something to the 6th power raised to the 1/3 power, exponent raised to an exponent, we multiply those exponents together, and 6 times a third is 2. So you can see where this value comes from. But if that does not make sense to you, it's not something you're going to be tested on. Separating the components out, x cubed, and x, each under their own cubed root symbol, may be an easier way to go about thinking about this. All right. Next two examples. Uh, Cubed root of a fraction. Once again, just like we handled the square roots, we can separate it into a cubed root up top and a cubed root down below. 216 is a perfect cube. When you take the cubed root, the answer is 6. And the cubed root of y cannot be simplified, so this is fully simplified. We don't have any radicals left in the denominator. And question D, we've got some constants and some variables that we're taking the cubed root of, so we can take the cubed root of the 8 and the x to the 4th. And in the denominator, we're taking the cubed root of 27 as well as the y cubed. In the denominator, the cubed root of 27 is 3. The cubed root of y cubed is just y. In the numerator, the cubed root of 8 is 2. And the cubed root of x to the 4th, if it helps you to think about it as being the cubed root of x cubed times the cubed root of just x, because 1 plus 3 is 4. So you're imagining kind of the 1 exponent there. Then we get the final answer of 2x times the cubed root of x over 3y as our final answer. All right, let's look at how we can add and subtract radicals. When you add and subtract radicals, you need to treat them just as like terms. Um, so if you think of this, if I just say the square root of 7 is x and the square root of 11 is y, then I can think of this as being 5x plus y minus 8x. I've just replaced my square root of 7's with an x, and I've replaced my square root of 11 with a y. How do I combine this? Well, I look at my like terms. 5 minus 8 is -3. Still attached to my x, needs to keep that same last name. And I just have positive y. Well, remember, my original expression didn't have x's and y's in it. It had square roots of 7's and square roots of 11's. So what I actually have is -3 times the square root of 7. And adding in that square root of 11. So this is our final answer. Okay, I did the 5 minus the 8 is -3, still times the same square root of 7, the same last name. And then I have just this one square root of 11 that can't be combined with the square root of 7 because it doesn't have the same last name. It's not a like term. One thing to be careful of, if you look at this radical and this radical, they seem to have different last names. They cannot be combined with one another, so it seems. However, and this is where we see why it's important to write radicals in simplest form, is these actually can be combined together. We can't tell yet because this second radical has not been written in simplest form. Once we write it in simplest form, we'll see that these two terms have the same last name and they can actually be combined together. So let's think about the square root of 20 as being the square root of 4 times 5. And then the square root of 4 is 2. And so you see that this can be simplified as 2 times the square root of 5. If we add this to our other term that we had before, 10 times the square root of 5, we see that when we add these together, we get 12 times the square root of 5. So there is a value to writing radicals in simplest terms so that you can see when you have like terms, like radicals, that can actually be added or subtracted from each other. We've been focused on square roots so far, but you can do the same thing with cube roots. If we've got 6 times the cube root of x plus 2 times the cube root of x, you just, again, kind of do this 6 plus 2 is 8, and we still keep the same last name times the cubed root of x. Okay. Now, I mentioned earlier that you cannot have a radical in the denominator when you're writing things in simplest form. All the examples we've seen so far, the radical in the denominator just kind of disappeared. That doesn't always happen. So how do you get rid of any radicals in the denominator? The strategy we're going to use here is we're going to multiply by fractions equal to 1. So for instance, just take an example here. If I have 437 as my starting number and I multiply by a fraction like 9/9, that fraction is equal to 1. And so really I'm multiplying by 9 and then I'm dividing by 9. I'm not doing anything to my 437 at all. The answer is still going to be 437. We're using the same idea here. We're going to multiply by a fraction that's the same on the top as it is on the bottom. So we're not numerically changing the value, but we are going to get rid of any radicals we see in the denominator. The easiest way to do this, remember we said that squares and square roots kind of cancel each other out. So if I take the square root of x squared, that just leaves me with x. It's like the squaring and the square rooting undo each other. So I can get rid of the square root of 3n in the denominator if I multiply the numerator and the denominator by the square root of 3n. what I end up with on top of the fraction is 5 times 3 is 15n, so I still have that inside the square root. But in the denominator, I now have the square root of 3 times 3 is 9, and n times n is n squared. So what I have is the square root of 15n in the numerator and 3n in the denominator. Now I've shown you where this 3n comes from. The square root of 9 is 3. The square root of n squared is just n. Sometimes it's actually easier for students to just say, okay, if I multiply the square root of 3n times the square root of 3n, I just get 3n as my answer. Sometimes that's easier to memorize. Sometimes it's easier for students to see where that comes from, actually doing the multiplication and getting 9n squared as your in-between step underneath the radical, and then taking the square root of that. The square root of 9 is 3. The square root of n squared is n. This is a straightforward process when you're dealing with square roots because you just need 3 times 3 so that you can take the square root and be left with 3. N times n, and you take the square root and you're left with n. It's a little harder with a cubed root because you need to multiply by the number that gives you the perfect cube. It's very easy to get the perfect square. It didn't take any thought to get the perfect square. Here, it requires some thought. What number is going to give us a perfect cube that we can easily take the cubed root of? So here, 9 is 3 times 3. It's not a perfect cube yet. I need to multiply by 3 one more time to get a perfect cube. So I'm going to multiply this fraction by the cubed root of 3 over the cubed root of 3. This is a fraction equal to 1. But importantly, what happened by choosing this number in the denominator, I'm now taking the cubed root of 27 in the denominator. So I have 2 times the cubed root of 3 in the numerator, but the cubed root of 27 in the denominator. So although there's nothing I can do to the numerator to simplify this, in the denominator, I now have the cubed root of 27, which is just 3. So this is as simple as I can make it. This is the final answer here. And we're finished with this question. So it's fairly easy to find the right fraction if you're trying to get rid of a square root in the denominator. It takes a little more thought if you're trying to get rid of a cubed root in the denominator. That's how you get rid of a root in the denominator if you have just one term in the denominator. What if you have two terms in the denominator? What if you kind of have like a polynomial in the denominator that has a radical in it? The strategy here that we use to get rid of radicals is to multiply by a conjugate. And a conjugate is to kind of a binomial expression, looks the exact same as the original expression, except you flip the sign to make it an addition sign becomes a subtraction sign, or subtraction sign becomes an addition sign. And so what we're going to do here is we are going to multiply again by a fraction equal to 1, but we're going to multiply 2 plus the square root of 3 over 2 plus the square root of 3. How did I choose that expression? Because it's the conjugate of what I currently have here in the denominator, 2 minus the square root of 3. So I flipped this sign on that binomial. So before I do the multiplication here for this polynomial that includes radicals in it, and remember, polynomials can't really include radicals, so I'm not really using the right vocab word here. Let's think back to what we learned in the previous couple chapters where we multiplied polynomials together like x plus 4 times x minus 4. Think about what happened when we used the FOIL method, the distributive method, to multiply these together. We did x times x is x squared. Then we did x times negative 4 is negative 4x. Then we did positive 4 times x is positive 4x. And then we did positive 4 times negative 4 is negative 16. Now, look what happened to those middle terms. Because the values in the first binomial and the second binomial were the same, just with opposite signs, those two middle terms are equal but have opposite signs. Therefore, they cancel out with each other. And the polynomial we're left with is x squared minus 16. We're going to do the same thing here. We're going to multiply this binomial times this binomial. And so let's focus on what we're going to have in the denominator. We're going to do 2 times 2 is 4. Then we're going to have 2 times positive root 3. So 2 times the square root of 3. Then we're going to have negative square root of 3 times 2, which is negative 2 root 3. And then negative root 3 times positive root 3 is just going to be, I'll go ahead and write it as minus the square root of 9 in case that helps, but that's going to work out to just be minus 3. In the numerator, if we fully multiply everything out, we're going to have 7 times 2 is 14. And 7 times the square root of 3 is 7 root 3. So let me just write this a little more simply one more time. 14 plus 7 root 3 over this term and this term. When we add those kind of roots to each other, they are like terms, so they cancel out. And we end up with 4 minus 3 in the denominator. Sometimes this extra step helps students, and sometimes it's just confusing. Some students prefer to just memorize, hey, there's this trick with conjugates. If I multiply two conjugates together, then I square the first term and I get 4, and I subtract, I kind of square the second term and subtract it. And the square root of 3 squared is just 3. So however you get to this last step here is up to you. Notice this can be further simplified. 4 minus 3 is just 1. And when you divide by 1, you don't do anything to the fraction. So the final answer is just 14 plus 7 times the square root of 3. So it's possible to get rid of even a more complicated fraction with a radical in the denominator that isn't by itself. It's being added to or subtracted from another value. Let's look at some real life examples of how we might use these use problems that involve square roots. If you're on the coast, kind of standing at sea level, and your eye is h feet above sea level, so maybe you're 5'6", so maybe your eyeballs are 5 feet off of above sea level. Estimate how far you can see when your eye is 5 feet above the water. So what we're doing here is we're saying the distance that we can see. 5 feet is my height. And h is supposed to be in feet. So I'm just going to plug that 5 in where I see the h. And that's the equation that I'm going to use. Now, is that equation simplified? No, not yet, but we've learned the strategies we need to use to simplify this. So we're going to end up with the square root of 15 up top and the square root of 2 down below. And now we can rationalize the denominator. We can get rid of any radicals we have in the denominator by multiplying by a fraction equal to 1. So I'm going to multiply by the square root of 2 over 2 because I know that the square root of 2 times the square root of 2 is just going to give me 2 in the denominator. And then in the numerator, I'm going to have the square root of 30. The square root of 30 is actually, in simplest terms, the prime factors are 2, 3, and 5. So there's no further simplification I can do there. There's no perfect square I can pull out of a 30. And so this answer is complete. or fully simplified. And if I actually wanted a number value, I could plug in the square root of 30 divided by 2 on my calculator and get a number value for that. Um, how about a golden rectangle problem? The ratio, length to width ratio of a golden rectangle is 1 plus the square root of 5, the quantity, divided by 2. And we're told that this Parthenon in Greece, the kind of front face of it forms a golden rectangle, and we're supposed to use this information to estimate the height of the Parthenon. And we'll set this up the way we learned some things in chapter 1 as setting it up as a proportion, setting two ratios equal to each other. So we're saying that 31 over h, this long side of the rectangle over the short side of the rectangle, is going to give us this same proportion, 1 plus the square root of 5 over 2. And we want to solve for h. Remember, you cannot solve for a value that's in the denominator. So our first step needs to be to get h up out of the denominator. One of the fastest ways to do that is just to kind of cross multiply here. So I'm going to do 2 times 31 is 62. And then on the right side, I'm going to have h times 1 plus the square root of 5. Now, I could use the distributive property and distribute the h out, but I don't actually want to do that because my goal is to get h all by itself. What I want to do is get rid of the 1 plus the square root of 5. So to get rid of the 1 plus of the square root of 5, I'm going to divide it away. But whatever I do to this side of the equation, I need to do to this side of the equation, 1 plus the square root of 5. And so this cancels out, and I'm left with h equals 62 divided by 1 plus the square root of 5. This is not in simplest form because I cannot have a radical in the denominator of a fraction. But this isn't a simple radical in the denominator that I can just multiply times the square root of 5 and get rid of it. That only works when I only have kind of one term in the denominator. Here I have an addition problem. So this is a situation that uses conjugates. So I'm going to multiply 1 minus the square root of 5. But to keep the equation the same, I need to multiply by a fraction equal to 1. So I have to do the same thing in the numerator that I'm doing in the denominator. So I'm going to multiply the top and the bottom times 1 minus the square root of 5 in parentheses. And in the numerator, I'm just going to have multiplying that out, that's going to be 62 minus 62 times the square root of 5. And in the denominator, 1 times 1 is just 1. And remember, the trick that we learned before, we're just going to square the square root of 5, which is just going to give me 5. And it's going to be subtraction sign between them. If you prefer to do this the way we did above, where you show every step in the kind of FOIL multiplication process, you can. And simplifying this further, I get 62 minus 62 square root of 5 over negative 4. And if I plug this in my calculator, I end up getting a value of about 19.16 meters. So that's how tall the face of the Parthenon in Greece is. I hope this helped.